Alright. So, time is short and it was my ambitious objective to give you overview of various aspects of equilibrium, non-equilibrium. Okay. So, non-equilibrium we started bit late, maybe 1/3 of the class. So, this is important topic which is not difficult, this is wave turbulence theory. In fact, it is much easier than what we did so far, but it is fascinating, it is also interesting. We can predict a lot of things with this weak turbulence theory. Okay. Weak turbulence, I am going to tell you what is weak turbulence in the next slide. And there are a lot of material, but I would say that if you want to look at it, well, my lecture notes should be okay enough for this course, because you do not have much time anyway to look at reference. But if you want to work on this topic, then you can look at them. Okay. So, this book by Nazarenko is one of the famous books on wave turbulence. Okay. So, I am just going to do formalism using several examples. Okay. So, this first PPT I am going to use a simple example which is not really a great example, but it is a simple example where I can do these calculations. Okay. So, the one main idea is that we have a linear term and a non-linear term. Okay. Here V is a constant. So, which is a linear term for this is a PDE, partial differential equation, like other equations we studied, and phi is my field unknown, phi is a dependent variable. Okay. Phi is function of x and t. So, this is a linear term and this is a non-linear term. If you like, you can put a factor lambda in front, or we do not need, because V is a parameter for me. So, I can say that this linear term is much bigger than the non-linear term. Is that idea clear? So, I assume that V d by dx this phi is much bigger than dx phi squared by 2. And this kind of things you done in your earlier course, where we did not deal with nonlinear equations, but you done this. Is a perturbation theory in quantum mechanics, right. We assume that the H naught, which is a Hamiltonian for the free thing, is large compared to H1, and H1 is a perturbation, right. So, in fact, this whole theory was developed by their few leading names. The one person who is given a lot of credit is Zakharov. So, these are from Russian school, okay. So, USSR school that time, earlier times, and by a lot of things happened in USSR, okay. I mean, well, Russia, because a lot of people left, Zakharov went to US after breakup of USSR, but like Landau, Kolmogorov, all these big names are from that Soviet school. And Zakharov is one such person. So, his idea was to use a quantum formalism and apply it to things like waves. So, waves, so if there is no nonlinear term, this kind of term, then wave will go unperturbed, just keep going. It may damp, but it will keep going. But when I put in the nonlinear term, the wave gets, in fact, the wave can generate more waves, and there is cascade of energy. And then what happens to turbulence property? In Navier-Stokes equation, when I did turbulence, where in fact there is no linear term for Navier-Stokes, right? The linear term is viscous term, which is small. So, for Navier-Stokes, our linear term is small compared to the nonlinear term, but now we are changing the role. We are saying linear term is big and nonlinear term is small, and that makes life, this wave turbulence life is simpler in some sense. Okay. So, please keep in mind that it is a wave turbulence, so their waves are essentially unperturbed. Well, waves are primarily unperturbed, there is some small perturbation, or these waves in ocean, they are essentially waves which are travelling, but the amplitude of the wave or their which keeps damping or it generates some new waves, but this generation process is weak. So, as I said, the nonlinear term is assumed to be weak compared to the linear term. So, nonlinear term does not affect the linear term. Okay. So, as a result, we do not denormalize V, this V will remain unchanged. Okay. So, RG is not required. Okay, so it's a great thing. No, the uh, uh, one major task of field theory is not required. So, if you recall, for Navier-Stokes equation we did two things. One was renormalizing the viscosity, a second compute the Kolmogorov constant using energy equation, energy flux equation. Here I need only energy flux equation, I do not need the renormalization. Okay. So, that is my way of looking at it. Okay. So, I am trying to make it simplified and also connect with what we have done in the course. But if you look at waves or look at Schrodinger equation, energy is conserved. No, Schrodinger equation is well, it's linear equation in fact, and there is a conservation of energy, conservation of mod psi squared. Okay, but so there is no in fact it turns out there will be back and forth of energy coming from in space. Okay, but I want to create a cascade. So, energy is going from large scale to small scale, then I need something. Okay, in Schrodinger equation typically, well, now there are systems which I am going to cover in the last lecture, nonlinear Schrodinger equation, which Sachin should come, well he is also missing. So, there is a cascade in quantum turbulence, but in if you look at Schrodinger equation, there are things will go to small scale, but they will come back, this is called revival. So, this is in Hamiltonian systems we cannot have decay or transfer of energy from one scale to next scale, detailed balance and so on will come into play. But in statistical physics we have many degrees of freedom, then is possibility. So, I think these are open questions, okay, there are people are working on them, but for our thing I would say that these are Hamiltonian systems, this will conserve energy, this equation which I have written on top, this will conserve energy. In fact, this is also Galilean invariant if you treat phi as a velocity field. Okay. In fact, V can be eliminated, that is why I said the toy problem I am doing it right now to illustrate some idea, it is not a great example. Okay. We need more complicated example which I will mention how to make it complicated, but for illustration this is okay. So, the idea is if I want to create a cascade which we want for turbulence, then I need some dissipation. So, we need small dissipation. Okay. Now, dissipation, what form of dissipation is not stated explicitly, it could be viscous term or it could be some term where I need to dissipate energy. Okay. So, this dissipation is not specified in the derivation, I am going to show you in when I derive it that where dissipation is coming, but you need this is normally hidden, but we need to know that there is a cascade and there is a dissipation. Well, cascade requires dissipation. Okay. Now, so it is a conservative system. So, this in fact you can prove that this is conserved, okay, that is conserved stuff. And so, cascades, in fact I am repeating this one. So, this part I just said a small amount of dissipation to set up a cascade, and most of the derivation which is done in weak turbulence theory assumes that cascade the energy flux is constant, and using this constraint we can derive energy spectrum. Okay. So, that is a typical framework, that is how we do it. So, and basically energy spectrum and scaling relations is obtained, and I am going to show you how to do it, it is not very complicated. Okay. So, I am going to use this example which is not the greatest example I told you, but it can help me to illustrate the ideas. Okay. So, let us calculate. So, first is this dispersion relation. Okay. This is called dispersion relation, you heard about this, no, frequency and wave number relation. How do you derive it? So, we write phi as phi k, well Fourier transform e to the power I k x minus omega t, right. In 3D is going to be k dot x. Substitute it here, this may give you I minus I omega, and this will give you V I k x, right. So, note the sign change, there is a minus sign there, there is minus sign there. Okay. So, frequency and k have different signs. So, this should be, ignore the nonlinear term, linear term, this is 0. So, that will give you omega equal to kx times v. V has the unit of velocity. Okay. So, this is dispersion relation. The first thing is you should know that is dispersion relation, the linear part. And then like we did before, I am going to write down the expansion. So, basically perturb the this nonlinear term. I am going to do Taylor I will basically write this convolution. So, write down the equation Fourier space, okay, in KT space. I am not going to do k omega. A lot of people do k omega, but KT is convenient for me. So, this is the equation in KT space, right. So, d by dt I will keep it there, okay, and this gradient d by dx will give minus ikx and phi squared will give me convolution, alright. Now, we need to write down equation for the energy. Remember, I am not interested in renormalizing this V, okay. So, why do I this equation is not of interest to me. Well, is interest to me, but I have to go to the energy equation. I will not carry this forward for Rg. For Rg, this is a starting point, no? Renormalization, right? I mean, remember, so we expanded this and then write Green's function and blah, 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 and that gives correction to V. But we do not do it here. I write down equation for the energy. So, what do? I multiply this by phi star of kT, correct, and add complex conjugate to it. So, plus complex conjugate. So, that will give me d by dt of mod phi squared, correct. Is it correct? I mean, d by dt of phi star will be give you phi star d by dt phi plus phi d by dt of phi star. But what happens to this term when I add complex conjugate? 0, it cancels, right, because look at it here is minus ikx v mod phi squared mod phi k phi square. Now, when I do the complex conjugate, then it becomes plus ikx, same thing, but this phi k square. When I add them, it becomes 0. So, this linear term in fact drops out, and the nonlinear term in the right hand side I will get triple phi q, phi p, phi q and phi star k, right. So, that is what we get. So, this algebra which we can easily do. Let me erase this stuff. So, the linear term has gone and this part, so is clear, no, I have phi p, phi q and phi star k, and I do complex conjugate adding, but there is a minus I sitting there. So, real part of minus I times some number, but then because of this I will get imaginary part of this triple correlation or triple term, okay. Right now I am not doing any correlation, but triple term, and the coefficient in front is kx by 2, this one, and this is the term called nonlinear energy transfer Tk. So, this phi k squared is changing with time, and because of this term nonlinear term. So, had it been a pure wave, Tk will be 0, right, pure wave means nonlinear term is 0. So, phi mod phi k squared does not change with time, but now we have the nonlinear term, that is why phi k changes with time, and this is the Tk, and this Tk which I have written it here, this Tk can, so I just rewrote that equation, and this Tk can lead to flux, right. Remember for Navier-Stokes there was a flux because of this nonlinear transfer. We have to argue that energy is going from a wave number sphere of radius k. This is a wave number sphere of radius k, then is energy going out, okay, and that is the flux, right, that is the definition of flux. So, I need to compute this Tk. So, let us compute Tk. Now, this is a cubic term, no, it looks pretty odd, I mean what to do with it. So, idea is do perturbatively. So, the idea will be to just, well, basically I am looking for average Tk. These are random things, so I am not interested in exactly detailed quantity as function of time. I am looking at time average and look at this statistical property. So, if assume that phi p, phi q, phi k is a Gaussian variable, that is a key part, okay. If it is Gaussian variable, then what happens to this cubic term, this triple term? 0, no, Gaussian odd order term is 0. Please at least learn this part from this course. Gaussian variable, all odd orders are 0, even orders can be written as product of second order. Okay. So, first order, so 0th order is 0, so I go to the next order. Okay. So, again we write the Feynman diagrams. So, the vortex is this term, this vortex, this is this vortex is kx by 2, and there are 3 phi's, phi q, phi p and phi k, okay, right, phi p, phi q and the phi star k, complex conjugate. Okay. So, I had to 0th order is 0, so I go to the next order. So, I write phi k as Green's function, this one, and so what will phi k give me? I will just write it here. Phi k is the non-linear term. The linear part will give only phi k. When I combine with them, they will give 0. So, linear part is not going to create any non-zero term. Okay. So, the non-linear term is g of k t minus t prime integral dt prime, exactly like what we did before, dt prime dt phi kt is, let me write it properly, phi kt. I will do complex conjugate bit later. So, there was a minus I k by 2, kx by 2, vortex term g k t minus t prime, Green's function t prime, and the nonlinear term. So, what is the nonlinear term within? So, do not use p and q, okay, you use phi of r t prime, phi of s t prime, and r plus s equal to k, correct. Now, you put a complex conjugate phi star, so this becomes plus and this phi star, right, and I need to integrate dt prime goes from 0 to t, and there is an integral of what, dr vector. Well, s is not an independent variable, s is k minus r, right, exactly same what we did before. Okay. So, I am expanding this gk in terms of Green's function. So, look what happens, I will get Green's function, and in the left there are 2 phi's, right, there are 2 phi's, phi q and phi p. From the right 2 phi's will come, these 2 phi's, this phi and this phi. How will you get non-zero value for this correlation and this correlation, this one? So, this is q, so this must be minus q, right, otherwise I will get 0. If this is p, then this should be minus p. So, that is c p, but this is t prime, okay, this t prime here, t prime, and here it is t. So, time are not equal. So, I write t minus t prime and t minus t prime. So, this is because of time dependent system. Okay, this is not like equilibrium statement, this is a non-equilibrium statement. Okay. So, t minus t prime, and this Green's function is t minus t prime. Of course, I need to do the t prime integral and the k, this p integral and also the r integral. Well, r integral is done here. So, if r equal to minus p, then what happens to s? S must be minus q. Okay. So, the Feynman diagram also tell you what should be the Way numbers. Okay. So, we got this one diagram. We will also have other diagrams. So, how many more diagrams? So, tell me how many more diagrams? 2 more diagrams. For phi q also I can expand by Green's function, and phi p also I can expand by Green's function. So, this Green's function and like that, and this Green's function like this. Okay. So, there are 3 diagrams, but let us focus on one of them. If you know how to compute one of them, you can do the computation for other diagrams. Okay. So, there is a dt prime integral, I forgot to put dt prime here, dt prime integral, and these 2 correlations and Green's function. Okay. So, remember what is the assumption I made for this time dependence? So, it comes from the linear term. By the way, my viscosity is not renormalized, my V is not renormalized. So, the Green's function will be very much e to power, well, you can look at the previous slide, is going to be, so our linear part will give me the Green's function, phi d by dt equal to minus I kx phi, right. So, Green's function is, we put a delta function. So, the time dependent part is basically the minus I kx t minus t prime, t greater than t prime. So, this is a theta function. Okay. So, this is part. So, we have, and then v will be there, the v there, v kx, no, dimensionally that must be. So, this velocity times kx. Everybody is happy with this? And we assume that the correlation function too have similar time dependence. So, this will give us exponential minus v times p t minus t prime, px, and this gives me v qx, and I do the time integral. So, that dt prime will go away, and this algebra is very similar to what we did before. So, this is that I wrote there, and the dt prime, I am always missing the dt prime, and that will go below, no, the exponential, and assume that t is bigger than this relaxation times, or not relaxation time, basically the wave times. This is a wave, no, right now. So, wave has a time period. So, I assume that this t is much bigger than time period, basically 1 by v kx, v delta k. Okay. So, v kx, okay. Basically there is a time period for the wave, and we are looking at last time where there are many oscillations of the wave have happened. Okay. Just put v of k. Okay, that has the inverse time, no, pk is inverse time. So, that will. So, if I make the assumption, then well, I am rewriting. So, this will come below. Okay. Now, whether waves, if I do the integral, then plus minus they do not cancel. So, I am going to put a damping, that part is critical. Okay. So, I said I need dissipation. So, to damp this wave I put minus epsilon t minus t prime. Okay. So, that is the wave part. So, this exponential, if it is oscillating, then these are oscillating waves, right. But I put this damping, then these oscillations will damp with time, like that, right. I mean, of course, you do not make epsilon small. So, damping is weak, but it will finally damp, otherwise this integral is not well defined. So, put this epsilon. So, if I do the algebra, then I get it below like that. Is that clear to everyone? So, that is the origin of dissipation. Okay, that dissipation is critical, otherwise this integral will basically 0. Look, in a conservative system there can't be a net energy flux. So, flux will be 0, but by this damping I put damping at small scales, and that will set up a cascade, and that epsilon is coming there. Okay, epsilon is basically damping at small scales. Okay. Now, what is this? You may recall we did in the complex variable course, complex variable lectures. So, this part I have in the next slide. So, I rewrite it, I multiply by I in top. Okay. So, minus I times I will become 1, and this I comes here. Okay. So, no, this is not I, 1 by x plus I epsilon is, this is a principal value 1 by x minus I pi delta x. I derived this, okay, and the principal value is 0 for this part. You believe me, the principal value is 0, plus minus cancel. For 1 by x, principal value is 0 anyway, right? Well, you will get things like 1 by x and 1 by x. So, if I integrate, sum it up, they will get cancel. So, this is the non-zero part. There is I here and there is I here, so that becomes minus 1. There is another I. So, how many i's are there in the top? 2 i's here, which is real, minus 1. There is another I here, which is a minus sign. So, I get imaginary part. Remember, I have imaginary part sitting in front. So, I will get a non-zero imaginary part by this trick. Okay. So, if I do all this algebra correctly, then I get this is a delta x. So, delta kx minus px minus qx, cp cq, which is coming from here, and this kx squared, and so this is my answer. Okay. So, this for one of the integrals I1. Now, it has two constraints. What is the constraint? K equal to P plus Q, because that is the momentum conservation, and this frequency also are matching, omega K equal to omega P plus omega Q. These are the two constraints you will find when in wave turbulence. Okay. It turns out for this case this can be derived from here, but in general it will not be the case, right, because if I take the x component I will get this x equal to Px plus Qx, and that is why I said what I am doing is very trivial example, but I want to, time is short, so I just want to give you a flavor of wave turbulence, but I will make it a bit complicated. Okay, and the last lecture will be some more complex examples of wave turbulence, but not too complex. Okay, so I will just try to simplify. So is it clear? So this is how I compute I1, and this integral will be non-zero. I mean, I did check, I can argue that this integral will be non-zero, but this is only one integral. In Feynman diagram there are two more. So as I put all of them together, then I get this three terms. Okay. So this is Cp Cq, but if I do the Feynman diagram for P part, then I get C. Well, I am sorry, this is a mistake here. P then Ck, this Ck, Cq Ck and Cp Ck. So this is stuff. I integrate it, I get Tk. Is function of k. But remember, we are looking at flux. So what is the flux? Flux is given Tk, I can define flux, which is energy going out of the sphere. So it is defined like this. Well, this works if I, well, this is the energy going out of the sphere. Okay. So Tk is energy coming into wave number k. If I sum over all the modes inside this stuff, is energy coming on to, if I sum over all this without a minus sign, what will that be? Net energy coming out in the sphere, right? This one, by definition, no, like everybody gets some money, okay, from the institute, the net money coming into the room. But what is the energy coming out of the room or money going out of the room? So you put a minus sign, right? I mean, if you are all spending, then there is money going out. So I put a minus sign, that is the flux. So there is another integral dk prime which will come, there is a dp integral, there is a dk integral, and it is going 0 to k, but dp is from full space. Okay. So this is the flux. Now this integral is complicated, well, I have not done it myself, but people have worked out similar integrals for different examples, but we do not want to compute the integral, I just want to get the form of Cp and Ck, that is spectrum, no, right. So I am looking for what is the form of spectrum, and that is when we will end the lecture in 10 minutes. So I want to, by dimensional analysis, I want to get the form of Ck, okay, assuming that this integral is finite and is constant, is independent of k, which is an assumption, may not work. Let us assume that this flux is independent of k, it is in some inertial range. Okay. So left hand side is epsilon, constant flux. Now this is Ck is the modal energy, energy per mode, and I define one dimensional energy Ek, which is Ck is Ek by k to the power d minus 1. Okay. I hope you remember this part. So energy, so Ek is the energy of a shell, right. So to get energy of a shell, I multiply the modal energy by the area of the shell, which is k to the power d minus 1. Okay. So this is one thing I need to use. So I need to replace them by this. And what is dk? I have it in my next line. dk is k to the power d minus 1 dk multiplied by the area, which is a non-dimensional number kd, right. So here I get k to the power d minus 1, and here I get below k to the power d minus 1. So this guy will cancel with that guy. Is that clear? When I will get dk here and dp here. So please look at this carefully, okay, you will get the right answer, no problem. This is one kx here and one kx here, and there is a delta function here. Okay. So we just need to count the dimensionally argument. Okay. So let us just do that here. So, this delta, so I am going to do it in the rough work here. Okay. So, there is 2 kx squared, no, this kx and kx, remember this kx is here, kx squared, and 2, so kd minus 1 cancelled, but here I have, so there is e squared, and what about here dk, so this dk has dimension of k, right. So, I will get dk and dp, but there is a delta function here, and what is the dimension of delta function? 1 by k. So, 1 by k will come and this will cancel with that, okay, and this 1 by v will come, right, this 1 by v is sitting there, v, pi has no dimension, so you can ignore pi. So, this one kx squared and this one k, so this k cube, e squared, which is e squared, 1 by v is epsilon. So, what do you get for ek? Ek is v epsilon 1/3, 1 square root k minus 3 half. Okay. So, this is one a famous energy spectrum formula. This was derived by Krecknen for hydrodynamic turbulence, not by this procedure, but some other procedure. But there is a mean flow comes into play, this mean velocity field v, this v is the mean flow, no. But more importantly, it comes in magnetohydrodynamics, Krecknen and Ereshnikov theory, which some of you have learnt about it. Krecknen and Ereshnikov theory, the derivation is bit more complicated because we have alpha in v is going in forward direction, backward direction, but what plays this important role is this v, alpha in wave speed. Okay. Interactions are more complicated and that is more realistic of alpha in waves, but this is the formula in fact we derived by for Krecknen, and I did it by pretty rigorous argument, except my equation beginning equation is not very good. Okay. So, in fact, for MHD we should work with z plus dot, the wave this is like a wave, and that should go as minus b naught dot k z minus z plus, and z minus dot equal to plus b naught dot k z minus. Okay. So, the minus here and the plus here. So, the two waves they interact in opposite direction, and that is more realistic, but this will involve more work. So, I can't finish it in a short time, but if I do it and the nonlinear coupling is z minus dot grad z plus, these are nonlinear coupling, not phi squared. So, my coupling right now is phi grad phi, okay, but here is a cross term. Okay. That is, if I do this stuff with this, then you will get the same result though. Okay. Now, this is one result, but there is another variation. Okay. If V is large, by the way, for weak turbulence we assume that V is large, right. V is large and the magnetic field is large, then the flow becomes 2 dimensional or quasi 2D. There is not much activity in the perpendicular plane. Then I assume this to be 3D, D, right now I assume that well D is 3, okay, for this flow, but then flow is 2D, then the spectrum changes. Okay. So, this is a theory by Galtier and Nazarenko, and the argument there is the following. Okay. So, here my spectrum is 2D, 2 dimensional, and then so this is not 3D. So, this dk per d. So, these are 2D. So, oops, okay, this 2D. So, my velocity field my phi field is in the plane. Okay. So, the 2D. So, D is 2, but interesting point is that here this integral is not for 3D. Okay. So, you can count dimensionally. In fact, I have done it here. So, 1 k from here, 1 k from here, okay, and this will cancel and the k squared here. So, you write as a, so I wrote dk as dk k squared, no, or k to d minus 1. Do not write that, right, you write k perp and k parallel, this one, and k parallel is cancelling with this delta, but k perp remains as is, or p perp remains as is, and that gives you dimension, which was in the previous slide I cancelled this with that, but according to these authors they said, well, do not cancel p perp, you cancel only px with that. Okay. If you cancel that but keep this, So, there is k here and there is k squared coming from here. Okay, so that is k4, and that E k squared according to this theory is k minus 2. Okay, this is because of quasi 2D. The spectrum has become 2D, and k perp and k parallel both had to be taken into account, and that gives you this spectrum. Okay. So, let us summarize my introductory thing on weak turbulence. Linear term is much bigger than nonlinear term. So, for MHD I need to assume that B naught is much bigger than fluctuations, and write down equation for the energy flux, assuming it to be constant, because all that derivation will not work if epsilon is also function of k, right. So, and then no renormalization of linear parameter. Okay. So, that is a good simplification, and that is a basic idea of wave turbulence. So, what I will do next is I will take some more examples like water waves. We can do rotating turbulence. So, I can just apply this idea without getting too much into detail. Some of it if you are not aware of rotating, well, you are aware of correlate force. So, I am just motivate the equation and derive the spectrum. It may look magical, but I hope you will get the idea. Okay, stop recording please.